Question number 5. A coil has a resistance of 10 ohms and draws a current of 5 amperes when connected across 100 volt 50 hertz source. Determine the reactive power of the circuit. Okay. So in this question, first of all, we should identify the load. Okay. So here it is given a coil has a resistance of 10 ohms. Okay. So it means that in addition to coil, it is having resistance. So it is RL load. Okay. First thing, this should be clear. Next is that it is connected to a voltage source of 100 volts and 50 hertz. This means that the supply source is having the RMS voltage of 100 volts. And since it is having the RMS voltage of 100 volts, so the current which is drawn is also RMS. We have to determine the reactive power of the circuit. Okay. So as I have mentioned in the previous class that if at all some particular power is given and asked, then we have to go for that power, else we can calculate the true power. So here we have to determine the reactive power. So in the power triangle which was explained in the theory, I have told you that if this is the power triangle, then this is the apparent power, this is the real power P, and this is the reactive power, and reactive power unit is VAR. Okay, if the magnitude is less, but if the magnitude is more, we can say it is kVAR. Okay, so here you can say this is the angle phi. So what is S? S is VI, volt amperes. Okay, where V and I are the RMS quantities, and RMS quantities, RMS voltage and RMS current is known to us. It is given here as 100 volts and 5 amperes. So what is Q? Q here is VI sin phi. Okay, so our aim is ultimately to determine this phi angle. If we can do so, then our problem will be solved. Okay. Similarly, I have explained you the impedance triangle. In this impedance triangle, Z is here, R is here, and X is here. Okay, with the same angle phi. So first of all, R is known to us, and coil impedance Z is V upon I. Okay, since we are talking of the IL circuit and we are talking of the total current which is flowing in the circuit. Okay, so we will, when we are talking of the total current which is flowing in the circuit, it means that we are calculating the, and we total current is flowing I. It means that this current I is flowing through the series combination of RL circuit, and it is flowing in the impedance Z. Okay, so what is Z? Z here it can be calculated 100 upon 5, so it is 20. Okay, 20 ohms. So next we have to calculate the angle phi. So if Z is known to us and R is known to us, then we can calculate the X easily by using Pythagoras theorem. This is one mode of doing the things. Next mode we will also discuss. So power factor is R by Z. R is 10, Z is 20, so it becomes 0.5. Okay, but since it's inductive load, so we have to mention that this power factor is lagging. Okay, we should always mention whether the power factor is lagging or leading, only then our interpretation about the power factor is complete. Okay, so this is the cos phi. So when cos phi is known to us, we can calculate the 1 minus cos square theta is equal to sin square theta, we know. So we can calculate the sin phi as 0.866 and substitute in the formula vi sin phi to get the result or the reactive power. Okay, since we are interested in calculation of sin phi and we are having this right angle triangle, so we know that sin phi is perpendicular upon hypotenuse. Okay, so x upon z. So using Pythagoras theorem we can calculate the x. Okay, so z square is equal to r square plus x square. Okay, so x will be z square minus r square. Okay, so it is 400 minus 100, which becomes 300, and when we calculate the 300, what we will get? 10 root 3. Okay, 10 root 3. Okay, so if we are going to calculate the so this is the x value. So now to calculate the sin phi, what is sin phi perpendicular upon hypotenuse? So this is our perpendicular and this is our hypotenuse. So 0 and 0 cancel out. So it becomes root 3 by 2. Okay. So this is the value of sin phi, and root 3 by 2, which is always, it is 0.866. Okay. So we can calculate using this method as well. Okay. The question says that what value of capacitance will have the capacitive reactance on 180 hertz, that is equal to 60 hertz inductive reactance of 0.061 Henry. Okay, so what is happening here? Here the reactance is same. Okay, so you can assume that there are two networks. One network is connected to 180 hertz and other is connected to 60 hertz, and 180 hertz is connected to the capacitor and this 60 hertz circuit is connected to inductor. Okay, so what is common in both these circuits, that their reactance is same. Okay, so the reactance of inductive circuit will be XL, that is equal to 2 pi FL, and everything is given to us. We will substitute. What we have to keep in mind is that we have to go by SI system. SI unit of inductance is Henry. So we have substituted this. If at all it was given as, say, in millihenry. Okay. Suppose it was given as 61 millihenry. Then we have to divide this value by 1000 to get its SI unit, so that we can substitute the value in the numerical. Okay, so here we have calculated the XL, and similarly what is the value of XC? It is 1 upon 2 pi FC. So only the unknown quantity is this capacitance C. When we are equating this XC and XL, we will get this value. Again, it is to be mentioned here that since we are dealing with the SI system, we will get the value of the capacitance in SI units only, that is farads. Okay, but since we are finding here that this value is very small, so we can present it as a in microfarads. Okay, so our numerical is telling us that an AC current when passed through a resistance immersed in water for 5 minutes just raised the temperature of the water to boiling point. When a DC of 4 ampere was passed through the same resistance under identical condition, it took 8 minutes to boil the water. Find the RMS value of current. Okay, so since on the passage of DC current and the AC current, the water is boiling at the same temperature, so we can say that the heat energy produced in both the conditions is same. Okay, so the heat energy is I square RT, resistance is common in both the cases, and energy is measured in joules. So since joules is the SI system of the energy, so when we are using the formula I square RT, the time is measured in seconds when we consider the SI system. So we will be using the same. Okay. So first of all, we have calculated the heat which is produced by the RMS current. So it is I square R and time is 5 minutes. So 5 into 60. So this is the heat energy which is produced. Now we consider the heat energy produced by the DC, that is 4 ampere current, and time taken is 8 minutes. So I square, that is 4 square into R into 8 into 60. Okay, so now both these equations, both the heat energy are same. So we will equate them, resistance get cancelled out, and we get the answer of RMS current as 5.06 amperes. Next numerical, here the instantaneous value of the voltage is given as 100 sine 100 t, and we have to calculate different parameters of amplitude, time, frequency, angular velocity, form factor, etc., etc. Okay, so here there is the direct application of the formulas. Just we have to remember the formulas and apply them. Okay, so the value, instantaneous value of the voltage is given. So here the maximum value is 100 volts. Okay, this is the maximum value. It is known to everyone. Okay, so first of all we have calculated this. Next is the calculation of frequency. So this is what we know. We know that this is 2 pi ft or sine omega t is all the same. So 100 is divided by 2 pi to get the frequency, or here we get the frequency in the SI system in hertz. Okay, but if we have to calculate the angular velocity which is in radians per seconds, so we will equate this instantaneous voltage by sine omega t, so it is 100 radians per second. Okay, and what is the time period? Time period, you know, is the inverse of the frequency. So frequency is known to us, 15.9. We will inverse to get the time period in SI system, and we can convert into in milliseconds if we desire so. Okay. So next is the RMS value. This we know voltage is 100. This is the maximum value. When we divide by root 2, we get the RMS value, and average value is 0.637 Vmax. So we can calculate the average value, and when we divide RMS value by average value, we will get the form factor, and peak factor is 1.414. It is constant for sinusoidal quantities. Okay, but if we are still required to represent this using formula, we can do using this. Okay, so in these sort of numericals, we have to identify the wave shape and act accordingly. Okay, so if we are to calculate the average value of the voltage over the whole cycle, so what is the difference between this and what we have derived earlier? 2 Vm 0 to pi, we have calculated the average value of the voltage over one cycle. Okay, 0 to pi we have integrated and multiplied by 2 because the wave shape is same, and divided by 2 pi. So we have got the same result, 2 Vm by pi. We have taken full cycle, but the wave form is also doubled, so the result becomes same. Similarly, we have calculated the RMS value and divided the both to get the form factor. Okay. For example, in next numerical, this is the half wave rectified output of rectifier, SCR, which you have studied in the previous class. So here the firing of the SCR is at pi by 4. Okay, so output we are having only for the limits pi by 4 to pi. Okay, so same we have to do to calculate the RMS values. Okay, sinusoidal value is same, Vm sin theta. So we have to square it, Vm square sin square theta d theta. Limits is pi by 4 to pi, and 1 upon 2 pi. When we are dividing by 1 upon 2 pi, we are calculating for the full cycle. As I have mentioned you earlier, that if it is not given in the numerical, then we have to calculate for the whole cycle. Okay, so we are dividing by 2 pi to get the average value, and then we will be doing the square root to get the RMS value. Okay, so similarly in the next numerical, what is happening, a DC current of 20 amperes is merged with the AC current of 20 sine omega t. Okay, so here what we will do, we 20 sine omega t we know, and since this DC current is added at every point, okay, so what we will do, first of all, we will add this 20 to this 20 sine omega t. Okay, so if we get the function of the waveform or the curve which is given, then rest is just the mathematical application. Here also our main focus was to calculate the current I. If we have calculated the current I, then we can easily calculate its RMS value, average value, form factor, peak factor, whatever is desired. Here we were required to calculate the RMS value. So I is known to us. We have squared it, applied the limits from 0 to pi of full cycle. To calculate the average, we have divided it by 2 pi, and then we have taken the square root to get the RMS value. Okay.